Hi everyone. So this video is the third of the Heap series of videos. In this video, what we're going to do is we're going to look at how to insert into a binary heap. So first of all, recall that a binary heap is a complete binary tree where heap order property is maintained. So the way we want to ensure that this happens on insertion is we ensure that the shape is maintained as well as the heap order property. Now, remember that a complete binary tree means that we fill in the nodes from top to bottom, left to right. So we cannot create a node on a lower level before we finish putting in every possible node in the level above. And we also have to put them in from left to right. Okay, so this is really important. This is something that we're going to be doing when we do the insertion. Okay, so let's begin by putting together this particular, let's walk through this algorithm together. So the way that we do insertion is we start by creating an empty node in the tree so that the tree stays complete, which means that we make the empty node in a way that the tree isn't going to be incomplete. We don't just put it anywhere we want. We put it exactly where the tree it needs to go for the tree to be complete. Now, remember, when we talked about complete binary trees, we actually said if a tree has n nodes in it, there's only one shape for a complete binary tree for that many number of nodes. There's only one shape for it to be because as you fill it out, it's top to bottom, left to right. So it's not like you can just create this empty node anywhere you want. There's only one place that the empty node can get created, which is at the leftmost position of the bottommost row that it has until it's completed, and then you can start a new row. Okay, so we place an empty node in the correct position to begin with. And then what we do is we say, okay, can I take the value and put it into this empty node that I just created? And if the answer is yes, great, put it in. If the answer is no, you can't put it in because it would break heap order, which is the second part. What you do is you take the parent and you pull it down into the node. And then you say, okay, can I put the value into the parent? And if the answer is yes, put it in. If the answer is no, again, you pull down that node's parent and keep going until you either place the value or you get to the root. Once the empty node is at the root, you have to be able to place the value in because there's nothing that is higher priority at that point. Okay, so let's take a look at how this actually works in action. Okay, because picture's worth 1,000 words, right? So we're gonna be using a min heap here, min heap, okay, which means smaller value has higher priority. So this is important because we need to define what priority means. Okay, so in other words, 1 has a higher priority than 10, which has a higher priority than 20. Okay, now let's put our data in. So keep this in mind. Smaller the number, higher the priority. So we start with push 10. Where will 10 go if we pushed it into the heap? Now the first one is pretty straightforward because the only node we can create is the root. So obviously 10 will go into the root. Now the next one, let's push 20. So 10 is here. Now we begin by basically saying, okay, let's add a node so that the tree stays complete. So pause the video, draw the node in for yourself. Okay, so if you drew the node over here, then you did it correctly. Okay. Actually, I did that too fast. So the node goes to the left-hand side of 10 because remember, we have to fill in our tree from left to right. Okay. So there are two possible positions that I could have placed the node, the one over here that I did do, or the one over here. But because for completeness, we have to go left to right, we have to choose this node to the left, not the one on the right. Okay, so left to right. Now, Can I place the 20 into the spot without breaking heap order? So remember, heap order says parent has higher priority, parent is higher priority than children. So this is the important part, that the parent has a higher priority. So does the parent have a higher priority? So remember, smaller value, higher priority. So does 10 have a higher priority than 20? Yes, it does. So we leave 10 where it is. We can just put the 20 in. Okay? So there we go. That is pushing 20. Now let's push 15. So here we go. Here's the tree that we start off with. Okay, copy, oops. Here's our tree. And where do we put the new node? So pause the video. Where would you put 15? Or where would you put the node first? Start with that. Okay. Now, the possible places are here, here, and here, right? Like those are the three places you can link a new node in this tree. However, for the tree to be complete, you cannot add a node to a lower level before you finish the current level. So remember, the level is the distance from the root. So the depth, remember. So you cannot add anything below 20 until you finish every node that is possible one above, which means that the empty node has to go over here. Now, can I put 15 in here without breaking heap order? So remember, so say yes or say no, okay? So know your answer, yes or no, can I do it? Now, remember, heap order says parent higher priority than child. So is 10 higher priority than 15? And if the answer to that is yes, you put it in. So if the parent's priority is higher than the empty spots, or the value that I want to insert, I should say, put the value into the empty spot. And it is. So 15 has a lower priority than 10. 10 has a higher priority than 15, so we can just put 15 here. Notice I never looked at 20. Okay, this is really important. I didn't have to look at its sibling. I don't have to look at this guy because it's not important. 20 is not part of the question. The question does not say, is the other node that is at the same level higher priority? The algorithm simply says parent, really important, parent is higher priority than children. That is heap order. That is the only thing that it says. It doesn't say sibling is higher priority. It just says parent is higher priority, okay? Okay, good. So let's try another one. Let's try push 12. Okay, so this is our heap so far. And I want to push 12 into this heap. What would I do? Okay, so pause the video, put your empty node in right now. Give you 5 seconds. Okay, so hopefully you've done that. The empty node goes to the left-hand side of 20. Okay, so remember, we filled out this node. We filled out this level. This level is filled. Obviously we filled out the root level. This level is filled. I cannot add any more nodes without making a non-binary tree, so we're done here. Now, at this level, remember that there are basically 4 places right now. And I have to create them from left to right. So the first one is going to go here. Okay? Now, can I put the number 12 into this node without breaking heap order? Okay? In other words, is 12's priority lower than 20's? Okay? So I'm not looking anywhere. I'm just looking at the parent. is this priority here lower, higher or lower than 12? Now, 20 has a lower priority than 12. So what we do is, if I put 12 in, it would be wrong because 12, the parent has to have higher priority, right? So what we do is we move the 20 down one level, okay, making 20's old spot the empty node. So now I have to ask, can I put 12 here without breaking heap order? Okay, is the parent higher priority than 12? Now the parent's value is 10, and 12, which is higher priority than 12. So yes, I can put 12 into this node, and we're good. Okay, so there's that. Okay, now what else can we have? Well, let's do a few more. Okay, so push. Let's see. Let's push 17. This one's easy. So, all right. What happens when we push 17? So here's the tree, and now I want to push 17 into it. Okay, pause the video. Where does the empty spot go? 5, 4, 3, 2, 1. 17 is going to go, well, the empty spot is going to start here, okay, to the right of the 12. Can I put 17 here without breaking any heap order rules? Okay, and the answer to that is yes. 17 can go here. Its parent, 12, is higher priority, so I can just simply put 17 right there. Okay, now let's fill out a few more. Okay, so here's my current tree. Actually, I'm going to redraw so that's not so gigantic. Okay, so 10, 12, and 15. Okay, 20, and 17. So this is what we have so far. Okay, so now this next example is push. Okay, let's push 8. What would this do, pushing 8? So pause the video, create your empty node, and then try to manipulate your tree so that it works, okay? So pause now. 5, 4, 3, 2, 1. The empty spot is going to go to the left of 15, okay? When you're drawing, be careful about left and right, that they actually really matter, so don't draw the line straight down, either to the left or to the right. Can I put the 8 into here without breaking heap order? Well, 15 is higher priority than, lower priority than 8. So if I put 8 here, I would break the rules, so I can't. So the algorithm says, take the parent, pull it down. Can I put 8 into this empty spot? And the answer is, well, no, because 10 is lower priority than 8. 8 is higher priority. Parent, higher priority, right? So we have to pull the 10 down to this empty spot. Oops. Now, can I put the 8 into this spot? Well, once we hit the root, the answer is always yes. So we put it in. So this is how we put in 8. We create the node, we pull everything down. What about, let's do a couple more, okay? So push, okay? Let's do 14. 14 for now. Oh, actually, no, let's do 20. Sorry, not 20, same value. Let's do 21, okay? So here is our tree. Okay, here's our tree. And I want to put 21 in. Where would you put it? Now, 5, 4, 3, 2, 1. So the empty spot goes into this spot right here. This is where the empty node is going to go first, the rightmost of this level. And we haven't filled it in, so that's why this is the last spot. Can I put 21 here without breaking any rules? Well, yes, because 21 is lower priority than its parent, 10. Okay, we only have to compare against the parent. If the parent is lower priority, or sorry, higher priority, 10 is higher priority than 21. So we can put it in, okay? So as long as the parent is a higher priority than the value we're putting in, we can just put it in, okay? So we're done. Now, that wasn't very interesting because there was no movement here. Oh, and this is 20. I somehow didn't copy the 2. Okay. Now, next spot. Next spot, I'm going to do 9. Okay, so here's the original tree. Okay. We're going to push 9. Now I want you to do exactly what we were doing, okay? Try it out for yourself. How do you create, what do you do first? What do you do second, okay? Where does the new node go? And then test and pull down from the parent as you go, okay? Okay, so 5, 4, 3, 2, 1. All right, so empty spot goes here because again, we filled out the previous level, so we're going into the new level and we go from left to right. Can I put the 9 here? Well, 20 is a lower priority than 9, so the answer is no. We have to pull the parent, oops, the 20, take the 20, pull it down into the current spot. This is the empty spot now. Can I put 9 here? Again, test the parent. Is the parent a higher priority or not? And the answer is no, the parent is lower priority. So we're going to pull the 12 down into this spot. Can I put the 9 here without breaking heap order rules? And the answer is yes. The parent has a higher priority. 8 is higher priority than 9. So we can take the 9, put it into this empty spot, and now we are done. Notice that actually this is not something to notice yet. So this is how we make this work, okay? So next one we're going to put in, we will put in 7. Oh, actually no, let's put in 5. So we're going to do 2 more, and then I'll give you sort of a quick summary test at the end. So we're going to push 5 first. Push 5. So here's our tree. What would happen if I pushed 5? Okay, so again, pause the video until you're finished. Start with this. Try to push 5, and then you can test the answer in 5 seconds. 5, 4, 3, 2, 1. So here we go. 5 is here. Oops, sorry. 5. So the empty node starts here. Can I put 5 in there without breaking heap order rules? And the answer is no. So we have to take the 12 and we have to move it into the spot. Can I put the 5 here? Well, 9 is lower priority than 5. So again, we move this down. Can I put 5 in that empty spot? And the answer is still no, because the parent 8 is lower priority than 5. So we move the 8 down. We've reached the root, so there's no more parent to compare against, and we put 5 at the root. Okay? Next, we have another one. So, by the way, what you will notice is that there is not necessarily an ordering left and right. First of all, notice that here, this is smaller than this one. But over here, this number, 17, is bigger than 15. 20 is bigger than 12. So if you're looking left to right, you're not going to see any pattern to it. You also cannot guarantee that something on a level is a higher priority than something on the next level. So for example, 10 is actually lower priority than 9. 9 is higher priority than 10, and yet 10 is higher up in the tree. So we cannot compare against this. We only care about parent higher than child. That is all we care about. Parent has higher priority than child. Doesn't matter what cousins and siblings and uncles and aunts have. Okay, like so we only look at parent-child relationship here. Now, next, so last one to look at. Okay. Uh, now let's look at the number 11. Push 11. Okay. So here is the tree. Oops. Copy. So what would happen if we pushed 11 into this tree? Okay. So go ahead, give it a shot. Okay. You have pause the video. Okay. 5, 4, 3, 2, 1. Okay, so where does 11 go? 11 goes to the left of 17. Oh, sorry, that's not true. 11 doesn't necessarily go there. So I have to move this around a little bit just to make space. So the node for 11 is going to go here, like on the first node, the empty spot goes here. Can I put 11 there? And the answer to that is no, I cannot. So what do? I take the 17 and I pull it, oops, I pull it down. So, oops, sorry. 11, and then, oops, sorry, not the 11. 17 is pulled down first. Move the 17 down. Can I put the 11 right there? Is 11 a lower priority than the 8? And the answer to that is yes. So again, you will notice that 11 is lower priority than 8, but it is not lower priority to the 9. Okay. Sorry, it is lower priority than the 9. It is not lower priority than 15 or 21. 11 is a higher priority than 21, right? So we still end up with this setup here, okay, where we only really care about values that are, we only care about comparing against parent. We don't compare against siblings, okay? Really, really important. So let's talk about, so this is sort of the last, actually, before we do that, let's take a look at why this was a good idea. Like, why do we just keep like having this empty spot and moving it? So let's consider what we have and why this is a good idea. If we have a tree, okay, so this is just any old tree, okay, with some nodes in it. Now, the first thing is that if it is complete, we have filled up this tree pretty much in its entirety except for the bottom level, right? So the first thing you need to know is the following. The number of levels in tree is log of n, where n is the total number of nodes, where n is number of nodes. Okay, so this is really important. Okay, it's the exponent you have to raise n to, raise 2 to in order to get n, right? So the number of levels in this tree is log n. Okay, so why do I care about this? Because and this is true because tree is complete. It's a complete binary tree. So that's why I can say this. If it wasn't complete, I cannot say this because remember, a stick is also a tree, right? So I can only say this because this is complete. Okay, so the fact that it's complete means that there are log n levels given where n is the number of nodes. Now, how do you know this? Well, you can actually do the math, right? So remember that you have, there's one node, right? And remember, for completeness, we have to do 2, okay? So the total number of nodes on level, okay? So the total number of nodes here is 1. The total number of nodes at this point would be 3. If I added another level, there are 4 nodes that I'm adding here. And so the total would be 7, okay? If I add another level, okay, there would be 8 nodes at this level. And there would be 7 plus 8, which is 15, right? So this is the total number. This is our n, okay? Now, interestingly, what is this number? Well, it's a little bit hard to see, but if you take a look, oops, here. What is another way? So we can look at it several different ways. So first of all, this is 2 squared minus 1. This is 2 cubed minus 1. This is 2 to the power of 4 minus 1. This is 2 to the power of 1 minus 1. Okay, so the total number, okay? So 2 to the power of 1 is 2, minus 1 gives you 1. 2 to the power of 2 is 4, minus 1 gives you 3. 2 to the power of 3 is 8, minus 1 gives you 7. 2 to the power of 4 is 16, minus 1 gives you 15. And in fact, this pattern continues itself. 2 to the power of 5 minus 1 will be 31. So if I add 16 more nodes here, it would be 2 to the power of 5 minus 1. Okay? So this formula right here tells me how many nodes there are. It depends on what level I'm on. So if I add another level, I can get up to 31 nodes. If I add another level beyond on that, I can get up to 63 nodes in the entire tree. And so the number of levels is the exponent I have to raise 2 to minus 1, okay, for that thing, which is why we can say that this is log of n. Okay. Now, log of n is a decimal, so we have to ceiling 4 minus 1, I think. It'll be 3 points. So ceiling, sorry, we have to ceiling it. We have to ceiling it to the next number. Okay, but subtract 1. So there's that. But in any case, this is actually, it doesn't matter. The minus 1 really doesn't matter here. The point is that we have log n levels to deal with. Okay. So what does all this imply? Well, if we are putting a node in, okay, if we can somehow just simply add a node anywhere at the bottom rightmost level, then once we have added this node, so here is my empty node. This is the empty node right here. What will happen after I put the empty node in? So we always say, okay, can I put the value in here? No, grab the parent, check the parent, and so on, right? So if we think about it, what happens is effectively this. We start off with our empty node being down here. And then we say, okay, can I put it in here? And if the answer to that question is no, we take it and we move our empty node up. Oops. We move our empty node up the tree. And if we can't put it there, we move it further up, right? So think of how we are moving this. Think of how we have to move this. Apparently very badly. Sorry, drawing programs are working. So, or I'm not drawing properly. So we start here. If it's not here, we check the parent. And if it's not there, we check the parent. And if it's not there, we check the parent. So because there are log n levels, the empty spot can only move log n times. So from the formation of the empty node to the point where we reach the root, we only have to check at most against log n values. because every time we do a check, we either put the number in or we move the parent down, right? And the empty spot effectively starts at the bottom and works its way up the tree. So since there's only log n levels, the empty spot doesn't have a lot of ways to go. It can only move up. Okay, remember that when we check, we never check against siblings. We don't care about cousins and uncles and whatnot. We only care about checking against the parent. So because the empty spot just moves in this straight line up, there is only log n steps that it can take before it gets to the point where it's at the root and we're done, right? So because of this, so what this means is that for us to do an insertion, push is log n, because so is push is O log n, because every time we do a push, we create an empty node, we simply check it against its parent all the way up the tree, and since there's only log n nodes along that pathway, you at most do log n comparisons and you're done. This is why this is fast. It's because we don't have to check every node. We only check against log n of them. Okay, this is the key. Okay, so this is how we actually implement insertion. Okay, now I'm going to do a quick sort of quick review with you right now. I'm going to put down a bunch of numbers and I want you to create a min heap out of these numbers. Okay, so get ready. Okay, and then I'll reveal the answer. So 16, 3, 9, 18, 4, 5, 7, 6, 20, 1, 15. Okay, so those are the numbers that I want you to try to put into your heap, okay, in that order. I'm going to start, I'm going to go 5, 4, 3, 2, 1, and then I'm going to do it as a check, okay? So try to do it first. Don't watch the rest of the video until you so pause the video now, and then check after you're done, okay? So in 5, 4, 3, 2, 1. So 16 goes in first, so 16 is at the root. Then remember, this is a min heap, so smaller value has higher priority. So we try to put in the 3. The 3 should go to the left of 16, but it can't because 3 is higher priority. So what do? We take the 16, we move it down, we put the 3 at the root. Okay? Now we try to put in the 9. Can we put the 9 in without breaking any rules? And the answer is yes, because the new node goes here, okay? And we can put the 9 in right away. What about 18? So the new node is to the left of 16. Can I put 18 in without breaking any rules? And the answer is, well, yeah, 18 can go in here, no problem. Okay? Because 16 is a higher priority than 18. Next one is 4. So can I put 4 in here? Is 16 higher priority than 4? The answer to this is no. So we're going to take the 16, we're going to pull it down one level, and now we're going to put the 4 into its place right here. Okay? 3 is higher priority than 4, so I don't need to deal with, I don't have to move the 3. So next one is 5. So can I put the 5 in here without breaking any rules? The answer is no, because 9 is lower priority than 5. So, oops, so we move the 9 down. Okay. So, oops, so the 9 gets moved down, and we can put the 5 into its place. Is 3 a higher priority than 5? Yes. So we put the 5 in. Now the 7. Can I put 7 in here without breaking any rules? Absolutely. Okay? Because 5 is higher priority than 7. So you will notice, okay, take a look at this diagram. The first highest priority is obviously at the root. The second is the 4. The third is the 5. The fourth is the 7. So in terms of where things are, 18 and 16 are significantly lower priority than 7 or 9, but it's both it's both it's all the same level. So that's something to keep in mind, is that um, we don't look left or right, we only look top to bottom. Okay, and again, if you look at here across the bottom, it looks like it's going from big to small, but up here is small to big, right? So you can't look left or right when you're doing this. You only consider parent-child relationships. So after 7 is 6. Can I put 6 to the left of 18? The answer is, of course, no, because 18 is lower priority. So we move 18 down. Can I put 6 in here? Is 4 a higher priority than 6? And the answer is yes, so we put it in. Next one is 20. So we try to put it into here, can we? And the answer is yes, we can. Next one is 1. Can I put 1 here? The answer is no. 1 has higher priority than 16, so move the 16 down. Can I put the 1 here? The answer is still no, so we move the 4 down because 4 is lower priority than 1. Can I put the 1 here? The answer is still no because 3 is lower priority than 1. So we put 1, we move it here, and then we have 1. And the last one, and then we're done, because once we reach the root, we're in. Next one goes here. Can I put 15 here without breaking any rules? The answer is yes, so we put it in. Okay, so this is basically how heaps works. Okay, so hopefully you got that. Okay, if this is your final answer, then you did it right. Okay, so in any case, next video is on how to do a removal, and then we will go on from there to talk about implementation.